Hello, everyone. Welcome to the ethics seminar series. Today, we are thrilled to have Dr. Clary Parkinson with us. It's fun that last week a lot of people asked me, is it real that Clary is going to be here? I said, yeah. So Dr. Clary Parkinson is a climate scientist and NASA Goddard, where she has worked since 1978. Her research is focused largely on sea ice and climate change, and has involved in computer modeling, Arctic and Antarctic fieldwork, and especially satellite data analysis. She has used satellite data to reveal the changes in Arctic and Antarctic sea ice since the late 1970s, including their long-term trends. In addition to her sea ice work since 1993, she has also been the project scientist for NASA's Earth Observing Aqua satellite since its launch in 2002. She has written books on satellite Earth observation, climate change, and the history of science, and has co-written and co-edited books on sea ice, climate modeling, satellite data, and the careers of women and Goddard. She is an elected member of National Academy of Engineering, National Academy of Science, the American Philosophical Society, the American Academy of Arts and Science, Sigma Xi, Phi Beta Kappa. She has a BA in mathematics from Wellesley College and a PhD in oceanography, climatology from the Ohio State University. So let's welcome the speaker.
Thank you, John. Very nice to be here. As John mentioned, I've been at Goddard since 1978. And at the time that I came, there were several satellites up collecting lots of data, and NASA had lots of data sets coming in from Earth observations. This was pretty new at the time. And so Dave Atlas, the director of the Goddard Laboratory for Atmospheric Sciences, was hiring lots of people and trying to make use of all these satellite data. And the two of the main ones, the ones that I've illustrated with here, one was the Nimbus 5 satellite, launched in December of 1972, and the other is the first Landsat satellite, which had been launched a few months earlier in July of 1972. So here is a picture of new employees at Goddard in the Goddard Laboratory for Atmospheric Sciences, 1978. As you can see, at that time, it was quite heavily dominated by males. Fortunately, a picture of new scientists at Goddard now would be much more evenly distributed. But there's several that some people might recognize, and so I'll just point out Lou Uccellini right there in the middle, who's now director of the National Weather Service. So the laboratory was hiring lots of people to look at lots of different topics from the satellite data. The topic I was supposed to be looking at was sea ice, and indeed that's what I've centered my career on all these 41 years that I've been at Goddard. So sea ice, for anyone who doesn't know, is ice that's formed in the sea, so it's got some salt content, not nearly as much as normal seawater, and it's pretty thin. It's nowhere near the size of icebergs. It's generally it's usually less than 3 meters thick, and even if it's just 1 meter thick, it can be safe enough to land a helicopter on. So it's thin, but important. And one of the reasons why it's important is that it does spread over a very large area. So here it shows in white, the area averaged over these 40 years, the area where there's ice in the summertime, and in white and green together, the area where there's ice in the wintertime. In the Arctic case, the wintertime ice coverage is about 15 million square kilometers. The area of the United States is 9.8 million square kilometers. So it's an area 1.5 times the area of the United States. And if you try to think of trying to get a data set for the United States day after day after day, and if there were no people living in the United States, like there are no people actually living on the Arctic sea ice, it really would be a task that would be extremely difficult if you didn't have satellites to get this picture for you. So the satellites have been incredibly important for us. In the Antarctic case, the wintertime ice is even more than in the Arctic case. Instead of the 15 million square kilometers in the Arctic, in the Antarctic, it's way up at 18 million square kilometers. Summertime, it's more like 5 or 6 million square kilometers in the Arctic, and these past few years, it's been even less. In the Antarctic, it's down lower at about 3 million square kilometers. And if you compare the two, you'll see that there's a huge difference in the geography. In the Antarctic case, there's a continent in the center of the South Polar region, and then the sea ice is not bounded to the north by land, whereas in the Arctic case, the sea ice is in the central portion of the Arctic, and it is bounded by continents. And so therefore, things are much more symmetrical in the Antarctic case than in the Arctic case. And part of the asymmetries are indicative of the connections between the ice, ocean, and atmosphere. In particular, no ice way up here north of Norway. This is very high latitudes to have no ice. Well, the reason is the Gulf Stream coming up and bringing the warm waters up. So the asymmetry is very much because of the geography, the land configuration, and what that does to ocean currents and the atmosphere. So it covers a huge area, and it also has a huge impact. And one of the main impacts it has in terms of climate is that sea ice is white. It reflects most of the radiation that's incident on it. If the sea ice goes away in an area, the solar radiation that comes down will mostly get absorbed in the ocean, stay within the Earth atmosphere system. So if the ice is here, the radiation gets reflected off, goes largely back to space. So retreat of the ice does mean more of the sun's radiation stays within the Earth atmosphere system, continuing to warm things up, and as a result, you get an enhancing or so-called positive feedback. Warming leads to less ice. The less ice leads to more warming because of the fact that more radiation is absorbed. So that's one huge impact on climate. But there are lots of other impacts that the sea ice has also, and here I've just indicated a few. Another climate impact is that it's a really strong insulator between the ocean and the atmosphere. And then it's got impacts on many different animals, polar bears in the north, penguins in the south, but whales and seals and many, many different animals, including microorganisms that live within the ice itself. So many impacts on animal life and, of course, impacts on humans as well. So as a result, sea ice was one of the things that NASA wanted to be observing with its satellite data. And here's a picture on the left of sea ice in the Weddell Sea, which is adjacent to Antarctica. from the Landsat visible imagery. And you can see sea ice shows up great in the Landsat images. The problem, though, is it's visible radiation, the same as our eyes. It has all the advantages of our eyes, but it also has the disadvantages. Disadvantage including the fact that if there's a cloud in the way, as in this case of the picture on the right, if there's a cloud in the way, the satellite will see the cloud instead of the sea ice underneath the cloud, just like our eyes would. And also, if it's dark out, then the satellite won't get a picture of the sea ice, just like our eyes wouldn't if it's dark out. And in the Arctic, in the middle of winter time, it's dark for months at a time. So this is a huge disadvantage. So for our climate studies, we do not concentrate on the Landsat data. Instead, we go to microwave data. The microwave data that we had at that time in the late 1970s was microwave data from an instrument called the Electrically Scanning Microwave Radiometer, or ESMR, on the Nimbus 5 satellite. And this was a proof of concept instrument. And it was great in terms of proving the concept that you could see the sea ice cover from the microwave data. And also other groups were showing that the microwave data proved useful for vegetation, for sea surface temperature, and for other things. So the proof of concept aspect of this instrument was fantastic, and we spent many years analyzing these data. But everything here that's in black means missing data. And so you could see that there's a lot of missing data. And these are 3-day averages, both of them. So even averaging over 3 days, you get a lot of missing data. Today's satellite instruments have almost none of these black areas, except right at the pole, where it's because of the orbit not getting right to the pole. So, so the instruments have been hugely improved. But even with the lack of, even with the existence of a lot of missing data, you can easily see where the sea ice edge is once you get used to these passive microwave data. And so it's right along here. So with the microwave data, huge advantage is that the sea ice really does look a lot different than the open ocean. Now, another factor about this particular instrument, the ESMR on Nimbus 5, is it only had one channel of information. So at first you could think, well, that's a huge disadvantage, and it is in many ways. You can only do one basic calculation. So with only one channel of information, we couldn't do things like we can today in terms of distinguishing first-year ice and multi-year ice and things like that. However, when you're just beginning to try to use satellite data or any kind of data for something, sometimes to have a smaller volume of data ends up being good. And so we could only basically do one thing, and what we did was we looked at the ocean area and we decided, well, we'll go with a tide point of about 135 Kelvin as ocean. We'll take the higher values for the sea ice cover and go with about 235 as full sea ice coverage and calculate the approximate indication of the concentration of the ice. And the concentration means what percentage of your grid cell is covered by ice. We'll take that and we'll do a linear distribution between the 135 as full ocean, 235 as full ice, and wherever you fall in that span is what the concentration will end up being. So it's a very simple calculation, much more simple than what we do now, when we've got multi-channel instruments. These were the people involved early on. Jay Zwally, myself, Joey Camiso, Bill Campbell, Per Glorson, Frank Carsey, and Don Cavalieri. And Bill and Per are deceased now. Jay, myself, and Joey are still working. And Frank and Don are both fully retired. So this is the type of picture we came up with by averaging for a whole month. And so that's why all that missing data area got filtered out, because we were taking a whole month. So this is the kind of picture we got. So the satellite was launched in December of '72. So our data set started with January of '73. We got a 4-year data set, lots of missing data in it, some whole months missing, but we got a 4-year data set. This was our first September. September is when the Antarctic ice cover is at its maximum. So this is what it looked like September of '73. And that looked pretty much what people would expect. The next 3 years had a huge surprise. '74, '75, '76 had this huge area, roughly twice the area of Illinois. So it's got this huge area of open water right in the middle of the ice cover. So a lot of people did studies to try to figure out, try to sort out what this might be because of. I had developed a sea ice model for my dissertation, so I used my sea ice model and moved the winds around and was able to simulate that kind of feature by moving the winds. Other people looked at the oceanography and decided it was more oceanographic. This is what the tabloid The Globe decided. So they claimed, well, there's a NASA photo, that's for sure. They also claimed there was a NASA scientist, but nobody had ever heard of the NASA scientist they mentioned there. But their rationale was, what else would be melting all this ice, except there must be some heat source underneath, and that would be a UFO base. So, but no NASA scientist ever confirmed that theory. And we continued, and we got out 2 books on this 4-year data set. The first was led by Jay Zwally, and it came out in 1983, and it was for the Antarctic ice. We did the Antarctic first because it doesn't have so much multi-year ice, and so therefore it didn't have that complication. And then I took over to lead the Arctic book, and that one came out then 4 years later in 1987. Fortunately, by the time those 2 came out, and again, we spent a lot of years doing those analyses, by the time they came out, we had a longer data set from the next satellite that was launched with this type of instrument, a passive microwave instrument. And that was the Scanning Multi-Channel Microwave Radiometer, or SIMR, on the Nimbus 7 satellite. And since then, the Nimbus 7 got a data set that went until August of 1987, by which time the Defense Meteorological Satellite Program had launched a Special Sensor Microwave Imager, or SSMI, and that sequence of the SSMI and its follow-on, the SSMI Sounder, or SSMIS, that sequence has continued to the present day. So the 40-year record starts with the SIMR and then with the SSMI and SSMIS, and that's the 40-year record starting from late 1970 on. Now, there are other similar instruments, in particular the Japanese launched the AMSR-E on the NASA's Aqua spacecraft back in May of 2002. And the Japanese have a follow-on to the AMSR-E called AMSR-2 on their own satellite, the Suzuku satellite, launched in 2012. So by the time we were done with the 2 books on the Nimbus 5 data, we had this longer record from Nimbus 7, and Don Cavalieri and I published a paper in 1989 showing these results for the Arctic. And there was a very slight decrease, certainly not something anybody would find very convincing in view of the interannual variability, but it was a decrease. And by that time, we all recognized that a lot of people were beginning to become concerned about global warming, and certainly a decrease in ice would go in line with global warming. So we realized we really wanted to continue this record as long as we could. So we made the effort of merging the SIMR and the SSMI records, and in 1999, 10 years later, we published this paper that showed these results for an 18-year record at that time. And you can see that when you're plotting monthly results, certainly what stands out is there's a lot more ice in the winter than in the summer, which is not something anybody would have questioned in the beginning. So we really wanted to see what the trends are. And in order to view the trends, we did a procedure called monthly deviations. And that takes out the seasonal cycle by, for instance, the first data point here is November of 1978. And so from that point, we subtract the average of all the Novembers and get this point there. And then December, we subtract the average of all the Decembers. And we go on through, so the monthly deviations, each month is just compared with that same time of year in the rest of the record. And so when we do that, removing the seasonal cycle, then it becomes quite clear that it's a downward trend. Now, it still wasn't entirely convincing, because there were some high values late in the record, but it certainly was clear that it was a downward trend. And that same year, a group from the University of Washington, led by Drew Rothrock, published a paper where they analyzed submarine data looking at the thickness of the Arctic ice, and they came up with a huge thinning of the Arctic ice from their early time period of 1958 to 76 to their later time period, 1993 to 97. So they came up with a huge thinning. Later they adjusted the numbers because they got more submarine data. The submarine data were being released bit by being declassified from the military. So they were released bit by bit, and when they got more data, it turned out the decrease wasn't, the thinning wasn't as much, but it was still a thinning. Well, the combination of these 2 papers, the satellite data showing that the ice cover was retreating, the aerial extent was getting less, and the submarine data showing that it's thinning, they combined together to make a much bigger point than either one of the 2 papers would have alone. And so these 2 papers got a lot of press coverage at the time, showing that Arctic sea ice decreases. Now, by this time, all sorts of other things had changed too. For one, many more people were concerned about global warming. For another, we had computers that could handle the satellite data very easily. For another, people had computers on their desks and could actually do calculations on their desks. So it was far, far easier for people to get the data, and the data were much better because these instruments have improved over time. So when I started in 1978, Goddard was kind of one of the very, very few places in the world where people could actually be handling the satellite data. By this time, 1999, people all over the world could be handling it easily and could easily get hold of it through the National Snow and Ice Data Center, which is where we always send our data for archival and distribution. So it made it much, much easier. Far more groups started using the data, analyzing the data, and it very quickly became such that lessened sea ice cover became kind of like a poster child for global warming. In huge contrast to in the 70s and early 80s, almost nobody even knew what sea ice was. Once when I was at a meeting and somebody was asking me what I worked on, and I said sea ice, their answer was, what's that an acronym for? So, so definitely things had changed. Things had changed quite a bit. So by now, and I don't know how to get rid of that. Does anybody know? Thanks. Okay. Okay. By now, so this is the 40-year record. And by now, the decrease in Arctic sea ice is so much more convincing because by now it's just overwhelmingly convincing that we've got a sea ice decrease. And this would be the monthly deviations. This would be the yearly averages. There are two places in particular where it went down so far that this was quite made a lot more interest both within the sea ice community and outside of the sea ice community, especially in 2007 when it went down so much more than it had ever gone down before. And it was at that time that a few people started saying we might see an ice-free Arctic within a decade. Now that hasn't happened. Fortunately, the sea ice cover went up again after that. But then in 2012, it went down even further. So those two, 2007 and 2012, and the minimum always comes in September. Here are the September, here are the minimum pictures for 2007 and 2012. And in this case, you could see you could easily have done a Northwest Passage right through there. And in the 2012 case, it would have been even easier to do a Northeast Passage where you could just easily sail through, whereas 2007, it would be a little bit harder to do the Northeast Passage. We do keep these numbers updated, and so this is from last Thursday. These, on the left, it's comparing this year so far up until last Thursday is in black on this one. And it's comparing it with the last 12 years. In this case, it happens to be in green, and it's comparing it instead with decadal averages and then with the 2 minimum years. So it's not a new record this year, but it's clearly on the lower end. But not a new record. Now, all of us have continued to do other things than just the sea ice extents. And for instance, Joey Camiso and Don Cavalieri both worked a lot with multi-year ice. Jay Zwally has used the laser altimeter data to look at thicknesses of the ice. And one of the things that I've done is to look at the length of the sea ice season. So in the picture on the left, 1979, it's how many days in the year had sea ice. And both in this case and in the ice extent case, the cutoff being used is 15%. So if it's got at least 15% ice coverage, I say, okay, we'll call that a day with ice. So for each pixel, you count how many days had at least 15% ice coverage. And this is the answer for 1979. Now, the SIMR instrument on the Nimbus 7 satellite did not get close to the pole. And so therefore, that's why this region of black here for no data is simply because the satellite did not get closer to the pole than that. The SSMI data gets a lot closer to the pole, and so the circle of missing data is much less. So this is 2013 data, and this is the use of those two words years is because this was from a paper published in 2014. And if you pay attention to the contrast between these two, you'll see that the season length has gotten a lot less. Now, in some areas like this is the Sea of Okhotsk. In some areas, it had quite a few days of, in fact, like over 120 days of ice, and in areas where it now, by 2013, had no days of ice at all. So a lot less ice, fewer days. So for each pixel, I took the trend at first through the first 10 years of data. And when I did that for the first 10 years of data, 79 to 88, when I did that, there's some areas of shorter sea ice seasons, some in the reds and browns and oranges, and some areas of longer sea ice seasons. And it's a little more shorter sea ice seasons, but there's still substantial areas that had longer sea ice seasons. And of course, the white in the middle simply is in all those regions and all that area, it didn't change at all because it was fully 365 days of ice in all the years. Now, when I do the same thing, but instead for the first 20 years of data instead of just the first 10, then it becomes more obvious that it's a lot more of shorter sea ice seasons and a lot less of the longer sea ice seasons. And then when I go to the 30-year trends, it's there are very few areas left that have longer sea ice seasons. And if we were to do the next picture, which would be the 40-year trends, even this area in the Bering Sea is no longer in the longer sea ice seasons. And the only areas left longer would be right along coastlines where there's land contamination that can affect the results. So in the Arctic, we have a very clear indication of lessened sea ice. This is part of a whole flock of changes in the Arctic that are all kind of coherent and along the lines of what was expected. The ocean's been warming, sea ice has decreased, and with the sea ice decrease, waves can get more easily to the coast, and so therefore there's increased coastal erosion. The atmosphere has been warming, the land ice has decreased, permafrost is thawing. So a whole sequence of different complementary changes in the Arctic. Now, when we turn to the Antarctic, things are very different. Okay, here is just a picture of the average of the month of minimum, which is February, and the average of the month of maximum, which is September. But now, when we do the same calculations as we do in the Arctic, now we find that the monthly averages, and of course the seasons are reversed, so now the high numbers come in September and the low numbers come in February. And it's not as obvious as for whether it's increasing or decreasing, though if you look closely, it does seem to be increasing a little. And here would be a picture of the trends once we do the monthly averages and the yearly averages. it was increasing up until 2014. And then in the next 3 years, it just plummeted, this huge decrease. And then it's come back a little. So very different from the Arctic, which was so understandable. Instead, we got changes in the Antarctic that were not expected. We did not expect these huge, did not expect this more than 30-year record of basically increases. The increases do come in every month, not just in the yearly averages. So here's each month and the trends for each month. And this is when you take the 40-year record. If we only took the record until 2014, which is when it reached its height, then it was looking much higher values for every single month, much higher values. But now, clearly with the reductions, it's gone down quite a bit. So to try to sort out the Antarctic, we do look at different regions, and in fact, we look at different regions in the Arctic too, but for the sake of saving time, I didn't put those up because they were very consistent of decreases in the Arctic. So, but however, in the Antarctic, there is one region, the Bellingshausen-Amundsen Sea region right here, that showed decreases, whereas the others show increases. And this does kind of help give some clue as to what's going on here in terms of one possibility. The Antarctic Peninsula is an area that has had temperature measurements made for quite a while because there's stations in the Antarctic Peninsula where they keep records. And there has been a warming in the Antarctic Peninsula, quite a bit of a warming in the Antarctic Peninsula. And so right close to the Antarctic Peninsula in the Bellingshausen Sea, the sea ice cover has decreased, which is right in line with the warming. Over other areas of the Antarctic, it's been more cooling, and so that makes sense that the sea ice would be increasing. There is an atmospheric phenomenon called the Amundsen Sea low pressure system, and a low pressure system in the Antarctic goes in a clockwise direction. So the winds would be coming from the north to the Antarctic Peninsula area and the Bellingshausen Sea area. Then they go over the very cold continent and come out over the Ross Sea. And so that is a possibility that changes in the strength of the Amundsen Sea low and persistence of the Amundsen Sea low could be contributing to lessened sea ice in the Bellingshausen Sea, increased sea ice in the Ross Sea. And the Bellingshausen Sea in the last few years has been more like on an increasing trend, whereas the others in the last few years have been more on a decreasing. So the Bellingshausen-Amundsen Seas is just out of whack with the rest of the continent. These are some studies, and I do have the full references at the end if anybody wants them, but these are some of the studies that have been, that tried to explain why the Antarctic sea ice was increasing so much, why it was increasing at all in this period from 1979 to 2014. And this shows a map of the trends in the length of the sea ice season over that period until the peak in 2014. And you could see that the sea ice season was decreasing in length in this Bellingshausen Sea area just west of the Antarctic Peninsula, but increasing over much of the rest. So the theories include, well, David Thompson and Susan Solomon connected it perhaps to the ozone hole and the polar vortex. Others, Sharon Stammerjohn connected it to the southern annular mode and the El Nino southern oscillation. John Turner and his colleagues connected it to the ozone hole and the Amundsen Sea low pressure system. Sigmund and Fife did a calculation where they discredited the ozone depletion as a cause And then Cecilia Bitz and her colleague Polvani, they did another calculation with a more refined model, and they also confirmed the Sigmund and Fife discrediting the ozone as a reason. Ventania attributed to basal meltwater from the ice shelves, and then this other one discounted that, and then Jerry Meal and his colleagues attributed perhaps to the interdecadal Pacific Oscillation and the Amundsen sea low. Definitely no consensus on what caused the increases in the Antarctic sea ice over this period. And while people were trying to explain the increases, then suddenly you got this huge decrease. This decrease was so great that it went from a yearly average maximum of 12.8 million square kilometers in 2014. In just 3 years to 2017, it went all the way down to its record low. I mean, it just didn't go down a little. It went below where it had ever been in terms of the 40-year record. This contrast, this net loss of 2.1 million square kilometers that happened in the Antarctic in 3 years, it took the Arctic over 3 decades to have a decrease that great. So a lot of press coverage has gone to the Arctic decreases, but the Antarctic did that amount of decrease in just 3 years. So it's just a huge, huge, huge change in the Antarctic over that 3-year period. But even with that decrease, the trend line for the Antarctic is still positive. So this shows that, again, we update. It's the same website that we update both the Arctic and the Antarctic on. And so this is up until last week, last Thursday. And then global. So when I add together the Arctic and the Antarctic, this is the global picture. One interesting aspect of the global picture is the average annual cycle. Smallest amount of ice globally is in February. And a lot of people say, no, that can't be, because February is the middle of winter. Well, the reason is because the amplitude of the Antarctic is so much greater, and that kind of overrides the fact that in the Arctic, the highest numbers are February and March. But globally, the lowest numbers in February and the highest are in October and November. So the annual cycle globally is kind of dominated by the fact that the Antarctic amplitude is higher, but the trend globally is dominated by the higher magnitude trend, and the higher magnitude trend is the Arctic. So the Arctic dominates in terms of the trend. And so this is the global trend, and you can see the clear decreases globally, and especially after 2004 when the southern hemisphere combined with the northern hemisphere for a really big decrease. So this shows, each dot shows a new record for that particular month. Arctic at the top, then the Antarctic, then the global. As I'm sure many of you know, like this past week, there were some record low temperatures, even though we know that in general it's been warming, but there were record low temperatures in many locations in the US and Canada this past week. Look at this Arctic picture. Not a single record low since 1986. Not one single record low, 75 record highs. This paper was published in 2016. If we were to add the other next 3 years to this plot, no new record lows, no new record highs, and 13 new record lows. So it's just incredible how every single month there's not one single new record high, whereas there are over 80 new record lows. In the Antarctic case, it's more of a mix, and if we were to add the next 3 years here, there are no new record highs, so no new blues, but there are several reds that come in here because of these decreases in the last few years. And globally, you can see that it's dominated by reds too for record lows. And these next 2 slides simply are to show that, I've got 3 slides left. These 2 are simply to show that 2 things that could be questioned, and we're showing that in this case that it really doesn't matter that much that we chose 15% as our cutoff. So in these 2 plots, the 15% curve is the top one, the 20% curve is the middle, the 30% curve is the bottom. And yes, the values are slightly different in terms of the trend lines, and certainly the numerical values are different. Like if you're accepting anything with 15% or more ice as ice covered, then of course it's going to be a higher number than if you're only accepting it if it's 30% or more. So of course the absolute values are different, but it's the trends that these lines are close to parallel. They're not exactly parallel. The numbers are somewhat different, but certainly whichever choice we were to make, 15, 20, or 30%, we're getting basically the same results. And then this is a study that Joy Camiso and I did to look at, does it really matter if we use a different algorithm? Because Joy does use a different algorithm than the rest of us at NASA use. And so we essentially showed that, no, it doesn't really matter all that much which of the different algorithms we use, and also different instruments. So we compared the AMSR-E instrument and the SSMI instrument. And again, the numbers are different. In fact, these numbers are more different than some of the others, but basically we're getting the same results. And both this curve and this curve, there are red and blue curves there, but you can hardly see the red curves in either case because they're so close to being right on top of each other. So, summary, sea ice is important. The satellites are incredibly valuable to us in terms of sea ice coverage monitoring. The Arctic has shown huge decreases. The Antarctic has been increasing largely until 2014, and then large decreases in the sea ice coverage. And the decreases in the Antarctic from 2014 to 2017 were just extremely large, way more than what we've ever seen in a comparable time period for the Arctic. And there's a lot of work ongoing to explain some of the things that we don't understand yet. Thank you.
Questions?
Thank you, Claire, for coming today.
Thank
it's
you.
a real pleasure to have you presenting here at ESSEC. So thank you very, very much. So a question, it was interesting how you described the 99 papers, Rothrock's and your own. Was it at that time that you really thought that, when was it that you really thought, okay, this is decreasing in the Arctic? At that time, I had just started my undergraduate degree, and I remember my professors in the UK were sort of hedging their bets. It's interannual variability, we don't really know. Was it at that time that you thought, yeah, this is looking bad, or was it later?
That certainly depends on the person. Some people were convinced at that time. I personally tend to be a more cautious person, and I was saying, I don't know. I mean, there's could be a cycle in here, and so I was interested in the results, but I was not 100% certain. Now, that same time, Koster-Vinikoff led a paper that I and Don Cavalieri and several others were a part of, and Koster was very convinced by that time, I think, and he was, well, Koster, you can speak if you want. But anyway, so
did you find, was it the 2007 minimum or by then, or what was it, you know, what kind of leads you to the conclusions that you have here, you know, in terms of the in terms of the Arctic? I mean, I know the Antarctic is confusing, but you know, I think it's interesting when so many of the different satellite signals are showing the same decline. I mean, for me, I'm not,
yeah,
like I'm convinced at this point, but I wasn't until recently.
Yeah, in line with my basic cautious nature, I have never been one to like project into the future, and so others of my colleagues have readily said that they expected like an ice-free Arctic at within one period or another, and I've always left it at there's so much interannual variability, I don't know, and I guess I would continue with that, and certainly in the Antarctic case, it seems to be way more erratic than in the Arctic case, and I sure don't know whether it's now on a downward trend that's going to continue or whether this is going to go back up again. The one other time period in either hemisphere where there was a really big change that would be comparable to what happened from 2014 to 2017 was in the mid-70s, and it was also the Antarctic, leading me to question, is the Antarctic maybe more susceptible to big, fast changes? And that case, in the 1970s case, it was also a decreased a lot, and George Kukla and Joyce Gavin from Columbia University, they published a paper that came out in 1981, and that paper showed this huge decrease, and some reporters ended up saying this could be the first real geophysical evidence of the global warming that some people were predicting at that time. Now, by the time that came out, the Antarctic had already, this Antarctic sea ice cover had already started rebounding a bit, and we at Goddard, Jay Zwally, myself, and Joey Camiso, we wrote a paper that then came out in 1983 showing that it had gone up a bit from the Kukla and Gavin results of 1981. So at that point, I mean, I realized, you know, just because there's a huge decrease doesn't mean you should jump to these conclusions like some people jumped at that one in the 70s. And it could be the same here. I mean, this maybe will have this similar rebound as what we saw in the 70s. It might be less likely because temperatures globally have been increasing, so it might have less of a chance to rebound, but it might rebound anyway. Thank you.
Is the dramatic draw-off of the ice concentration in Antarctic has any connection with the iceberg breakoff in the 2018 recently?
The icebergs, huge as they are, they don't end up being area-wise of a magnitude that would indicate this. But as they melt, they're melting freezing cold water into the oceans. And so from that respect, they could be a factor. They could be a factor. But in general, the people who have tried to explain this, and there are several who have tried to explain it, they're explaining it more on the basis of various oceanographic and atmospheric phenomena. Yes.
The deduction or the decrease of the as extents are more anthropogenic or a large-scale climate variability or natural variability?
I think in the Arctic, it is definitely tied to warming of the Arctic, and it's definitely a feedback effect. So the warming is greater because the sea ice has decreased, and the sea ice is decreasing because it's warmer. In the Arctic case, I would say that yes, there's probably an anthropogenic contribution in terms of humans are pouring greenhouse gases into the atmosphere, and that certainly has a tendency to warm the atmosphere. And so I would say that's an element of what's going on. But climate change has been going on for the whole history of the Earth, and so not all climate change is due to humans, but I would say that this warming probably, most likely, is humans are an element of that warming.
All we are talking here is about extent. It's just area. And could you say something a little about what sea ice mass, volume in Arctic and Antarctic?
Okay. We do calculations also on the areas. I've just put up the extents because of limited time, but also I feel that those are a little bit more sound numbers than the areas. But in terms of the volume, that's an extremely important calculation. We do not have the basis for a 40-year record for the volume because we don't have the thickness. The thickness now, we are going to get a good record of thickness, and that's going to be because we do have satellites up there now. The Europeans have radar altimeters. Goddard, NASA has a laser altimeter on the ICESat-2 satellite, and those will eventually get us, we hope, a really good record of the ice thicknesses throughout the Arctic and the Antarctic sea ice cover. But in terms of a long-term record, they just don't go back far enough. And so what does go back further would be the submarine data. But the submarine data, it's like you got one straight line here, and then another straight line there, another straight line there, some months with nothing. And so the submarine data are so much less complete than the satellite data. So for the ice volume, it's really important to get, but we haven't gotten it yet for a long record. With ICESat-2 and with Cryosat, we're getting there.
Any other questions? Let's conclude and thanks the speaker again.